Hey everyone, this is Dr. Walker. In this video, we're going to go over another example of applying Gauss's law to a problem with planar symmetry. In this example, we have to find the electric field due to an infinite plane of positive charge with uniform surface charge density sigma. So I've written down Gauss's law, and the first step is to figure out what kind of Gaussian surface that we're going to use. And we know that the electric field comes out perpendicular in either direction away from this plane of charge. That helps us figure out what our Gaussian surface is going to be. So what is typically used is actually a cylindrical box. And I've seen an actual rectangular box used, but I learned to do it with a cylindrical box. It doesn't make any difference. So the condition for the cylindrical box is that the ends of it are parallel to that plane of charge, and that the long sides of it are perpendicular to it. So let's see why this is a good choice. Well, the field is going to be constant through all of the ends. As you can see over here, we're the same distance away from the plane, so the electric field is going to be constant here, it's going to be constant here. And also, the electric field is parallel to dA. In both directions, the dA points away from the ends. So when we're looking at the integral in Gauss's law, the electric field comes out, and we want to integrate over the area. So the area of one of these ends is A. So we can just say A, but then we'll also have to look at the flux through the other area. And so we can just double it and say 2EA. And that will be the total flux. We don't have to worry about the curved surface because the electric field is parallel to the curved surface at all points. None of this electric field, whichever way it's going, none of it goes through the surface since it's parallel. So there is no flux through the curved surface, only through the ends. So we have two ends that we have flux through, so 2EA on the left side, and then we need the charge enclosed. We know that surface charge density is defined as charge per area. So within our Gaussian box here, sometimes called a Gaussian pillbox, well, the area enclosed is going to be the same area as the ends of the cylinder. So we're going to say that the charge enclosed is going to be sigma A. It's a thin plane here, so it just has that area A of charge, and divided by epsilon naught. And now we're almost done. We can actually eliminate the area, and this is why it doesn't matter if you do a cylinder or a rectangular box, the area cancels out, and we can solve for the electric field. It's going to give us sigma over 2 epsilon naught. And so this is the result. This is the magnitude. The direction is away from the plane. What is really significant about this result is that we see that it does not depend on the distance. That means no matter how far away that you are from this plane, that is the magnitude of the field, and that means that the field is uniform away from this plane of charge.